The closest star to Earth isn't the Sun. Most people don't realize this, but somewhere in the southern sky, if you know where to look, if the night is dark enough and you're in the right hemisphere, you can see it. It's faint, so faint that most people have never noticed it. It's called Proxima Centauri, and it's only 4.24 light years away. At this very moment, photons from Proxima Centauri are traveling through space toward you. They left the star about 4 years ago. In a few hours or days, when conditions are right, those photons will reach your eyes if you know how to look for them. You'll see a faint red star, nearly invisible to the naked eye, but real nonetheless. That faint red dot is our nearest stellar neighbor. That's the closest star to Earth besides the Sun, and it's positioned to be humanity's first target for interstellar exploration when technology advances far enough to attempt the journey. But Proxima Centauri isn't traveling alone through space. It's part of a system, a trio of suns bound together by gravity. The Alpha Centauri system, as it's known, consists of three stars performing an elaborate gravitational dance that has continued for billions of years and will continue for billions more. Understanding this system, what it contains, how it formed, whether life might exist within it, is one of the great challenges and obsessions of modern astronomy. For as long as humans have looked at the night sky, we've wondered about the stars. Ancient astronomers cataloged them. Medieval scholars contemplated their nature. Copernicus and Galileo revolutionized our understanding of the cosmos. Newton explained gravity. Einstein explained space-time. And yet, despite millennia of study and scientific advancement, the stars remain profoundly mysterious and wonderful in many ways. Their distant light still captivates us. They call to us. What are these distant objects? Are they like our sun? Do planets orbit them? Could life exist on worlds circling distant stars? These questions have captivated human imagination for centuries. And now, with modern technology, we can begin to answer them, beginning with our nearest stellar neighbor, Alpha Centauri. That might sound far. Light travels at 299,792 kilometers per second. A light year is the distance light travels in 1 year, about 9.46 trillion kilometers. Multiply that by 4.24 and you get 40 trillion kilometers. That's incomprehensibly far. It would take the fastest spacecraft humans have ever built, the Parker Solar Probe, about 73,000 years to reach Proxima Centauri. It would take the fastest crewed spacecraft we currently have, the Space Shuttle at maximum velocity, about 1.5 million years. Yet in cosmic terms, Proxima Centauri is absurdly close. It's our nearest stellar neighbor, and it's not alone. Proxima Centauri is part of a triple star system called Alpha Centauri. The system contains three stars: Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Together, these three stars form the closest star system to Earth, a mere 4.37 light-years away at their center of mass. This is the story of Alpha Centauri. The nearest star system, the one most likely to be visited by human spacecraft in the distant future. The system we know most about outside our own solar system, it's a story of three suns, of planets orbiting distant stars, of habitable worlds that might exist in the habitable zones of these stars. It's a story about distance, about exploration, about what it might take to reach the stars. Let me start with the most basic question. What is Alpha Centauri? Alpha Centauri is a triple star system. That means it's not one star, but three stars orbiting around a common center of mass. The three stars are Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and Alpha Centauri B are much closer to each other than either is to Proxima Centauri. Alpha Centauri A and B orbit each other at a distance varying from about 11 to 35 astronomical units, about the distance from Earth to the Sun to the distance from the Sun to Jupiter. They complete one orbit around each other every 79.9 years. This orbital period is remarkable in that it's measurable within a human lifetime. Astronomers observing Alpha Centauri over the past 200 years have watched the two stars move through their orbit. In the early 1800s, the two stars were at their closest approach. They've been moving apart ever since and won't be close again until the year 2060 or so. Astronomers are looking forward to observing the next close approach, as it provides an opportunity to measure the star's masses with extraordinary precision using Kepler's laws. The orbit of Alpha Centauri A and B is elliptical, not circular. At their closest approach, they're about 11 astronomical units apart. At their most distant separation, they're about 35 astronomical units apart. This variation in distance means that any planets orbiting one of the Alpha Centauri AB pair would experience varying levels of radiation and gravitational perturbation from the companion star. The orbital geometry creates a complex dynamical environment. This complexity is actually interesting for habitability. If planets exist around Alpha Centauri A or B, they would need to maintain stable orbits despite perturbations from the companion star. This constrains where planets could orbit. Planets could orbit close to their star, so close that the companion star's perturbation is negligible. Planets could also orbit around the common center of mass of both stars, at a very large distance where both stars' gravity would be relatively stable. But the intermediate zone, distances comparable to the AB separation, would be chaotic, with planetary orbits gradually becoming unstable. This actually limits the habitable zone regions around Alpha Centauri A and B. The habitable zones I mentioned earlier, about 1 to 1.6 astronomical units for Alpha Centauri A, about 0.67 to 1.03 astronomical units for Alpha Centauri B, are in the intermediate zone where stellar perturbations could be significant. Whether this would destabilize planetary orbits over long timescales, millions of years, is a question that requires detailed dynamical simulations. Proxima Centauri, by contrast, is very far from Alpha Centauri A and B. Its distance from the Alpha Centauri AB system varies from about 3,200 to 17,000 astronomical units. So far away that light from Proxima Centauri was not even recognized as being part of the Alpha Centauri system until 1915. Proxima Centauri takes millions of years to complete one orbit around the common center of mass of the whole system. The Alpha Centauri AB system is itself orbiting around something. We live in a galaxy, and all stars in the galaxy orbit around the galactic center. The whole Alpha Centauri system is moving through space, orbiting around the center of the Milky Way along with billions of other stars. Now let me discuss the individual stars and their properties. Alpha Centauri A is very similar to the Sun. It's a G-class star, which means it's a medium-sized, long-lived star like our Sun. Alpha Centauri A is actually slightly larger and more massive than the Sun, about 1.1 times the Sun's mass. It's slightly brighter than the Sun, about 1.5 times as luminous. In many ways, Alpha Centauri A is what we might call a solar twin, or a solar analog. It's not identical to our Sun, but it's similar enough that we can use our understanding of the Sun to understand Alpha Centauri A. This similarity makes Alpha Centauri A particularly interesting for the search for life. If life could exist in a solar system orbiting our Sun, could it not also exist in a solar system orbiting a star very similar to our Sun? The conditions would be roughly equivalent. The energy output would be similar. The timescales for planetary evolution would be similar. Alpha Centauri B, by contrast, is different. It's a K-class star, an orange dwarf. K-class stars are smaller, cooler, and less luminous than solar-like stars. Alpha Centauri B has about 0.9 times the mass of the Sun and about 0.5 times the luminosity. It's dimmer and cooler than the Sun, and it will live much longer. Whereas the Sun has a main sequence lifetime of about 10 billion years and is currently about 4.6 billion years old, Alpha Centauri b could live for 15 billion years or more. It's a younger, more stable star that could provide a stable environment for planetary systems and life for an extraordinarily long time. Proxima Centauri is even smaller and dimmer. It's an M-class red dwarf, the smallest type of star that undergoes hydrogen fusion. Proxima Centauri has only about 0.12 times the mass of the Sun. It's so small that an object would have to fall toward it from a very close distance to reach its surface. Yet, despite its small size, Proxima Centauri is not insignificant. It has a surface temperature of about 3000 Kelvin, hot enough for thermonuclear fusion of hydrogen into helium in its core. What makes Proxima Centauri remarkable is its extreme longevity. Red dwarfs like Proxima burn their fuel incredibly slowly. Proxima Centauri could continue fusing hydrogen for trillions of years, far longer than the current age of the universe. This means that life could potentially exist around Proxima Centauri for unimaginably long periods of time, much longer than the current age of the universe, potentially as long as the entire future lifetime of the universe before stars burn out. Now let me discuss the discovery and observation history of Alpha Centauri. Alpha Centauri has been known since ancient times. The two brightest stars, Alpha Centauri A and B, are visible to the naked eye from the southern hemisphere. They appear as a single bright star to the unaided eye, though a small telescope easily resolves them into two separate stars. The ancient Egyptians and Greeks knew of these stars. They called them by various names. The system is called Alpha Centauri because it's the Alpha, the brightest star in the constellation Centaurus. The recognition that Alpha Centauri was a binary star system, two stars orbiting each other, came later. In the 17th century, as telescopes improved, astronomers began to resolve binary star systems. The brighter members of the Alpha Centauri system were among the first binary stars to be resolved with a telescope. Understanding the true distance to Alpha Centauri came much later. Measuring distances to stars was one of the great challenges of astronomy. For centuries, astronomers had no way to measure distances beyond our solar system. The concept of parallax, the apparent shift in position of a nearby object against distant background objects when viewed from two different locations, offered a way to measure stellar distances. In 1838, Friedrich Wilhelm Bessel used parallax measurements to determine the distance to 61 Cygni, which was the first star to have its distance measured. The parallax method works by measuring the position of a star against distant background stars at 2 points in Earth's orbit around the Sun, 6 months apart. The tiny shift in apparent position between these two measurements, combined with knowledge of Earth's orbital radius, allows calculation of the star's distance. Alpha Centauri's distance was measured using similar parallax methods. Modern measurements have refined the distance to extraordinary precision. Alpha Centauri is 4.367 light-years away, with an uncertainty of only about 0.002 light-years. This is an incredibly precise measurement for something so far away. The discovery of Proxima Centauri came later. In 1915, Robert Innes discovered that there was a third star in the Alpha Centauri system, a faint red dwarf he named Proxima Centauri. The name Proxima literally means nearest. Proxima Centauri was 0.11 light-years closer to us than Alpha Centauri A and B, making it the closest star to Earth. The discovery of Proxima Centauri was surprising to many astronomers. Proxima Centauri is so much dimmer than the other two stars that it's not visible to the naked eye. Its faintness made it undetectable until photography improved enough to capture its image. The discovery showed that there were stars fainter than we could see with our eyes, nearby stars hiding in plain sight. Now let me discuss what we've learned about planets in the Alpha Centauri system. For decades after its discovery, Alpha Centauri was thought to be a star system without planets. Early attempts to detect planets around Alpha Centauri yielded no results. The planets were too small and too faint to detect with the methods available at the time. The challenge of detecting exoplanets is profound. An exoplanet orbiting a distant star is trying to hide behind the overwhelming light of its host star. Imagine trying to see a firefly near a searchlight from miles away. The firefly's light is billions of times dimmer than the searchlight's. Direct imaging, actually photographing the planet, requires specialized techniques and adaptive optic systems to suppress the star's light and reveal the planet's faint glow. Several methods exist for detecting exoplanets, and each has strengths and limitations. The transit method, also called the photometric method, works by measuring the dimming of a star's light when a planet passes in front of the star from Earth's perspective. The planet blocks a tiny fraction of the star's light, causing a measurable dip in brightness. This method works best for planets in close orbits around their stars, where transits happen frequently. The radial velocity method, also called the Doppler method, works by measuring the motion of the star induced by the planet's gravity. A planet's gravity pulls on its host star, causing the star to wobble slightly. This wobble causes the star's light to shift slightly toward blue when the star is moving toward us and slightly toward red when moving away from us. The Doppler effect. Sensitive spectrographs can measure these shifts with extraordinary precision. The radial velocity method was how Proxima Centauri b was discovered. The planet's gravity causes Proxima Centauri to wobble back and forth with a velocity of just 1.4 meters per second, slower than a walking pace. Yet spectrographs can measure this velocity shift by detecting the Doppler shift in the star's spectrum. Over many observations, the periodic nature of the velocity variation reveals the presence of an orbiting planet. Other detection methods include astrometry, which measures the position of a star as it wobbles due to planetary gravity, microlensing, where a star system's gravity bends and magnifies light from background objects, allowing us to infer the presence of planets. And gravitational wave detection, which theoretically could detect planets through subtle space-time distortions, though this remains purely theoretical for exoplanet detection. Each method has advantages and disadvantages. The transit method works best for planets close to their stars and with stellar radii favorable for detecting transits. The radial velocity method works for planets at any orbital distance and is not limited by the star's radius. Astrometry requires very precise position measurements, but is not limited by orbital parameters. By using multiple methods, astronomers gain complementary information about exoplanetary systems. In 2016, everything changed. Using the European Southern Observatory's HARPS spectrograph, astronomers detected a planet around Proxima Centauri. The planet was named Proxima Centauri b. Its discovery was announced with great excitement because Proxima Centauri b appeared to be potentially habitable. Proxima Centauri b is an Earth-mass planet orbiting in the habitable zone of Proxima Centauri. The habitable zone is the region around a star where liquid water could potentially exist on a planet's surface. Not so close that the planet overheats and water evaporates, not so far that the planet freezes solid. The habitable zone around Proxima Centauri is very close to the star. Proxima Centauri is much dimmer than the Sun, so the habitable zone is at a much smaller orbital distance. Proxima Centauri b orbits at only about 0.0485 astronomical units from Proxima Centauri, about 12 times closer than Mercury is to the Sun. The orbital period is only 11.186 Earth days. Proxima Centauri b completes one orbit in about 11 days. This close proximity raises interesting questions about what Proxima Centauri b might be like. At such a close distance, Proxima Centauri b might be tidally locked, meaning the same side always faces Proxima Centauri, just as the same side of the Moon always faces Earth. If Proxima Centauri b is tidally locked, one side would be perpetually phasing the star and receiving intense radiation, while the other side would be permanently in darkness. However, tidal locking is not certain. Proxima Centauri is known to be an active star, producing stellar flares. These flares could potentially have heated Proxima Centauri b strongly enough in the past that the planet's rotation would have been affected. Additionally, if the planet has a dense atmosphere, atmospheric circulation could transport heat from the day side to the night side. Beyond Proxima Centauri b, astronomers have discovered other planets in the system. In 2020, another planet was detected around Proxima Centauri, Proxima Centauri d. This planet is more distant from Proxima Centauri than Proxima Centauri b, with an orbital period of about 5.1 years. Proxima Centauri d appears to be a super-Earth or mini-Neptune, somewhat larger and more massive than Earth. Searches for planets around Alpha Centauri A and B have also been conducted. No confirmed planets have been detected around these stars yet, though searches continue. This is not surprising. Detecting planets around Alpha Centauri A and B is more difficult than detecting them around Proxima Centauri because Alpha Centauri A and B are much brighter, making the subtle signals of orbiting planets harder to detect. Let me now discuss the characteristics of Proxima Centauri b in detail, because this planet represents humanity's nearest confirmed exoplanet. Proxima Centauri b has a mass of at least 1.27 Earth masses, according to the best current estimates. It orbits in the habitable zone of Proxima Centauri, meaning it receives an amount of stellar radiation roughly comparable to what Earth receives from the Sun. The planet's orbital period is 11.186 days. It completes one orbit around Proxima Centauri every 11 days. The surface of Proxima Centauri b is unknown. We cannot see the surface directly from Earth. The planet is too small and too faint. We know its existence only through the Doppler shift it induces in the light from Proxima Centauri. The star appears to wobble slightly as the planet's gravity pulls on it. Given the mass and the assumption that the planet is rocky like Earth, we might estimate Proxima Centauri b's radius to be somewhat larger than Earth's. If Proxima Centauri b has a thick atmosphere, it would appear larger. If it lacks an atmosphere, it would appear smaller. These details matter for understanding whether the planet could harbor life. One possibility is that Proxima Centauri b is covered in water, a water world. Another possibility is that it's similar to Earth, a rocky world with continents and oceans. A third possibility is that it's completely dry, a barren desert world. Without more data, we cannot distinguish between these possibilities. The atmosphere of Proxima Centauri b is also unknown. Earth's atmosphere is primarily nitrogen and oxygen, with trace amounts of carbon dioxide and other gases. The atmosphere was produced by life and geological processes. We don't know what Proxima Centauri b's atmosphere would be, or even if it has an atmosphere at all. The stellar environment around Proxima Centauri is harsh. Proxima Centauri is an active star, prone to violent outbursts called stellar flares. These flares release tremendous amounts of energy, including ultraviolet and X-ray radiation. A stellar flare from Proxima Centauri could potentially strip away the atmosphere of Proxima Centauri b if the planet's magnetic field is not strong enough to protect it. Earth is protected from the solar wind by Earth's magnetic field. The magnetic field deflects charged particles away from the planet. Without this protection, the solar wind would gradually strip away our atmosphere. Proxima Centauri b might have a similar magnetic field if it has a liquid iron core that generates planetary magnetism. Or it might lack a magnetic field, leaving its atmosphere vulnerable to the stellar wind from Proxima Centauri. Despite these uncertainties and challenges, Proxima Centauri b remains fascinating because it's the closest known potentially habitable exoplanet. If life exists anywhere beyond Earth, Proxima Centauri b is the most accessible target for study. Let me discuss why Alpha Centauri matters for human space exploration. Alpha Centauri is the closest star system to Earth. While 4.37 light years is an incomprehensible distance for human civilization as it currently exists, it's the closest we have to a neighboring star system. Any plans for humans to travel beyond the solar system would most likely target Alpha Centauri first, simply because it's closest. The idea of traveling to Alpha Centauri with human astronauts has captivated imaginations for decades. Various concepts have been proposed. The slowest would use conventional rocket propulsion, but as I mentioned, this would take 1.5 million years with current technology. That's clearly impractical. More advanced propulsion concepts have been proposed. Solar sails could use the radiation pressure from a star's light to accelerate a spacecraft. Theoretically, a solar sail of sufficient size could reach a significant fraction of the speed of light. Project Breakthrough Starshot, announced in 2016, proposes to send small probes to Alpha Centauri powered by laser-driven light sails. The concept envisions kilometer-scale light sails carrying gram-scale probes, accelerated by a powerful ground-based laser array to a velocity of about 20% the speed of light. Such a probe could reach Alpha Centauri in about 20 years. Other concepts have been proposed. Antimatter rockets would provide tremendous thrust by annihilating matter and antimatter, releasing energy according to Einstein's E equals mc squared. However, antimatter is incredibly difficult to produce and store. Current technology can produce only tiny amounts of antimatter. Fusion rockets would use controlled nuclear fusion to accelerate reaction mass. These are theoretically possible, but remain far beyond current technology. Warp drives, which would distort spacetime to allow faster-than-light travel, remain purely speculative and may violate fundamental laws of physics. For now, the most realistic near-term concept for reaching Alpha Centauri is some variant of light sail propulsion or advanced rocket designs based on physics we understand. A crewed mission to Alpha Centauri would require solving problems beyond just propulsion. Life support systems would need to sustain human astronauts for the multi-year journey. The psychological challenges of traveling for years in a confined spacecraft toward a destination the travelers would reach only at the end of their lives would be immense. More realistically, any first human contact with Alpha Centauri might come through automated probes sent ahead, followed eventually by human exploration if technology advances sufficiently. Let me discuss the travel times to Alpha Centauri at various velocities. At current spacecraft velocities, reaching Alpha Centauri would take roughly 1.5 to 2 million years. This is far beyond any practical human timescale. The entire history of human civilization is less than 10,000 years. Waiting 1.5 million years is incomprehensible. At velocities proposed for advanced future spacecraft, say 10% the speed of light, the travel time would be about 43.7 years. This is a long time, but it's within the lifetime of a human astronaut. A space traveler leaving Earth at age 40 might reach Alpha Centauri at age 84 if they could maintain the journey over that period. At velocities envisioned by Project Breakthrough Starshot, about 20% the speed of light, travel time would be about 20 years. This is starting to approach realistic timescales for human space exploration, though still far beyond current capabilities. At 50%, the speed of light travel time would be about 8.7 years. At the speed of light, which is impossible for massive objects but is a useful benchmark, travel time would be 4.37 years, 1 light year per light year of distance. The energy requirements for accelerating a spacecraft to high velocities are immense. A spacecraft with a mass of 1,000 kilograms accelerated to 10%. The speed of light would have kinetic energy of about 4.5 times 10 to the 18th power joules. For comparison, the entire annual energy consumption of human civilization is about 6 times 10 to the 20th power joules. Accelerating a spacecraft to 10% the speed of light would require about 0.75% of humanity's annual energy consumption. This is enormous, but not impossible in principle for a future advanced civilization. Now let me discuss what we can observe about Alpha Centauri from Earth and what future observations might reveal. From Earth, we can observe Alpha Centauri using telescopes. We can measure the positions of the stars, measure their brightness, analyze their spectra, and search for planets. Each new observation provides more information about this nearby star system. Parallax measurements have allowed astronomers to determine the distance to Alpha Centauri with extraordinary precision, better than 0.5% uncertainty. Spectroscopy has allowed measurement of the star temperatures, composition, and rotational velocities. Photometric observations have revealed that Alpha Centauri A and B undergo small brightness variations as they orbit each other, occasionally passing in front of each other from our perspective. These transits allow measurement of the orbital parameters with high precision. The search for exoplanet transits around Alpha Centauri A and B continues. If a planet transits in front of one of these stars from Earth's perspective, the brief dimming of the star's light would reveal the planet's size and orbital period. So far, no confirmed transits of exoplanets have been detected around Alpha Centauri A or B, though observations continue. Future observations with more powerful telescopes will provide even more information. The James Webb Space Telescope has observed Alpha Centauri. The Nancy Grace Roman Space Telescope, when it launches, will have unprecedented capabilities for detecting faint objects. The extremely large telescope and similar ground-based observatories will provide detailed spectroscopic observations of the Alpha Centauri stars. Direct imaging of exoplanets around Alpha Centauri might eventually be possible with future telescopes. Directly imaging an exoplanet is extraordinarily difficult because the planet is so faint compared to its host star, like trying to see a firefly next to a searchlight from miles away. Yet, with advanced technology, direct imaging might eventually become possible. Let me discuss the habitable zones of the Alpha Centauri stars in detail. The habitable zone is defined as the region around a star where liquid water could potentially exist on a planet's surface. The habitable zone depends on the star's luminosity and temperature. A hotter, brighter star has its habitable zone farther from itself. A cooler, dimmer star has its habitable zone closer to itself. For Alpha Centauri A, which is similar to the Sun but slightly brighter, the habitable zone extends from about 1.07 to 1.63 astronomical units from the star. This is slightly farther from Alpha Centauri A than Earth is from the Sun. For Alpha Centauri B, which is dimmer than the Sun, the habitable zone extends from about 0.67 to 1.03 astronomical units from the star. This is closer to Alpha Centauri B than Earth is to the Sun. For Proxima Centauri, which is much dimmer than the Sun, The habitable zone extends from about 0.039 to 0.097 astronomical units from the star. This is incredibly close. Mercury orbits at 0.39 astronomical units from the Sun, so Proxima Centauri's habitable zone is much closer to the star than Mercury is to the Sun. These habitable zones define where planets could potentially have liquid water and thus could potentially harbor life. A planet in the habitable zone of a star receives an energy flux comparable to what Earth receives from the Sun. However, the habitable zone is not a guarantee of habitability. Many other factors affect whether a planet can harbor life. The planet needs to have a protective magnetic field, or a thick atmosphere, or both to shield life from stellar radiation. The planet needs to have geological processes that recycle carbon and regulate temperature, processes collectively called the carbon cycle and related feedback mechanisms. The planet needs to remain geologically active, but not so active that it's constantly bombarded by volcanoes and earthquakes. And of course, even planets meeting all these criteria might still lack life if the origin of life is rare. Now let me discuss stellar activity and radiation from the Alpha Centauri stars. All three Alpha Centauri stars produce radiation across the electromagnetic spectrum. They emit visible light, ultraviolet radiation, infrared radiation, and radio waves. The amount of each type of radiation depends on the star's temperature and activity. Alpha Centauri A is similar to the Sun in its activity. The Sun produces occasional solar flares and coronal mass ejections, sudden releases of magnetic energy from the Sun's atmosphere. Alpha Centauri A likely produces similar phenomena. Alpha Centauri B is less active than Alpha Centauri A. Being cooler and smaller, it produces less violent flares and less energetic outbursts. Proxima Centauri is known to be highly active. Observations have revealed frequent stellar flares from Proxima Centauri. These flares release energy equivalent to powerful solar flares from the Sun, except Proxima Centauri produces them more frequently. A single stellar flare from Proxima Centauri can increase the star's brightness in ultraviolet light by a factor of 1,000 or more. The high stellar activity of Proxima Centauri raises questions about the habitability of planets orbiting the star. Intense ultraviolet and X-ray radiation from stellar flares could damage biological molecules. Charged particles from flares could strip away planetary atmospheres. However, planets around active stars could also potentially have protective mechanisms. A magnetic field generated by the planet's interior could deflect much of the particle radiation. A dense atmosphere could shield the surface from radiation while still allowing visible light to reach the surface. Life on such planets would need to be robust, adapted to the energetic environment. Stellar flares on Proxima Centauri have been studied extensively. Observations show that Proxima Centauri can increase its brightness by a factor of 1,000 or more in ultraviolet light during a major flare. These flares release energy equivalent to the Sun's entire energy output over several seconds. The implications for Proxima Centauri b are significant. A flare's radiation travels at the speed of light, reaching Proxima Centauri b in minutes. The charged particles from the flare's eruption follow more slowly, taking hours to days to reach the planet. If the planet has a magnetic field, it would deflect most of these particles. If not, they would strike the upper atmosphere, potentially damaging atmospheric chemistry and ozone layers. The cumulative effect of frequent flares is important. If Proxima Centauri produces major flares multiple times per year, the cumulative energy received by Proxima Centauri b from flares could be substantial, potentially exceeding the energy from Proxima Centauri's normal emission. Life on Proxima Centauri b would need to tolerate this energy flux or evolve mechanisms to protect against it. Some scientists have modeled how planetary atmospheres respond to stellar flares. Simulations show that an Earth-like atmosphere could withstand stellar flares from Proxima Centauri, though the upper atmosphere would be significantly affected. The ozone layer, which protects Earth's surface from ultraviolet radiation, would be periodically damaged by flares, but would gradually recover between flares. Life on Proxima Centauri b, if it exists, would need to be radiation resistant or underground, or the planet would need a very thick protective atmosphere. Water also plays a role in protection. If Proxima Centauri b is a water world with deep oceans, life in the oceans would be protected from radiation by the water column. Even a few meters of water provides substantial shielding from ultraviolet radiation. Deep ocean life would be relatively safe from stellar flares, even if surface life would be devastated. This raises an interesting question. If Proxima Centauri b is a water world, where would life be? Life in deep oceans would need an energy source. On Earth, deep ocean life around hydrothermal vents gets energy from chemical reactions, with hot mineral-rich water emanating from the planet's interior. Could Proxima Centauri b support similar life? Possibly. Proxima Centauri b likely has sufficient internal heat due to tidal heating, the friction generated by Proxima Centauri's gravity pulling on the planet. This tidal heating might drive geological activity and hydrothermal systems. Now let me discuss the future prospects for exploring Alpha Centauri. Robotic probes could reach Alpha Centauri before humans. A probe powered by light sails, as envisioned by Project Breakthrough Starshot, could reach Proxima Centauri in 20 years. Such a probe would be tiny, perhaps no more than a few grams, comparable in size to a postage stamp. Despite its small size, it could carry scientific instruments capable of taking images, measuring radiation, and detecting planetary properties. A probe reaching Alpha Centauri could directly observe Proxima Centauri b and any other planets in the system. It could measure the planet's sizes, temperatures, compositions, and atmospheric properties. It could search for signs of life. It could analyze the radiation environment around the star. The data returned from such a probe would be revolutionary, expanding our understanding of exoplanet systems beyond what current telescopes can achieve. After robotic probes, human exploration might eventually follow. But this is speculation far into the future. Any crewed missions to Alpha Centauri would require technologies far beyond what currently exists. A more intermediate step might be more powerful telescopes capable of observing Alpha Centauri planets in greater detail. Future telescopes, perhaps built in space or on the moon to avoid atmospheric distortion, might be able to directly image Alpha Centauri planets and analyze their atmospheres for signs of habitability or even biosignatures, chemical signals indicating the presence of life. Let me discuss the search for life in the Alpha Centauri system. If life exists anywhere in the Alpha Centauri system, it would most likely be on Proxima Centauri b or around Alpha Centauri a or b. Life would need liquid water, moderate temperatures, and protection from radiation. These conditions could exist on planets in the habitable zones of these stars. The origin of life is still not fully understood. On Earth, life emerged from non-living chemistry sometime in the first few 100 million years after the planet's formation. Whether life's origin is easy or difficult remains debated among scientists. Some argue that life emerges readily whenever conditions are suitable. Others argue that life is rare, requiring a fortuitous combination of circumstances. If life is common, then the Alpha Centauri system might harbor multiple biospheres. If life is rare, then Alpha Centauri might be devoid of life, despite having potentially habitable planets. The search for extraterrestrial life in the Alpha Centauri system remains speculative. We have no confirmed evidence of life beyond Earth. But the search continues through observation and through theoretical study of the conditions necessary for life to emerge and persist. Some scientists have proposed that if advanced civilizations exist in the Alpha Centauri system, they might communicate through technological means. Radio signals, for example, could potentially be detected. Searches for technological signals from Alpha Centauri have been conducted as part of the broader SETI, Search for Extraterrestrial Intelligence program. So far, no confirmed signals have been detected. Now let me discuss the scientific mysteries that remain about Alpha Centauri. Despite extensive study, many questions about Alpha Centauri remain unanswered. Does the Alpha Centauri AB binary system have planets? Searches have been conducted, but no confirmed planets have been detected around these stars. Either planets are rare around these stars, or planets exist but haven't been detected yet due to limitations of current detection methods. Are there more planets around Proxima Centauri beyond Proxima Centauri B and D? The discovery of multiple planets is important for understanding planetary system formation. Each new planet discovery provides constraints on how planetary systems form and evolve. What is the atmospheric composition of Proxima Centauri B if it has an atmosphere? Spectroscopic observations could potentially reveal atmospheric composition by analyzing how the planet's atmosphere absorbs light from Proxima Centauri as it passes in front of the star. Such observations are extremely challenging, but might become possible with future telescopes. Is Proxima Centauri B tidally locked, or does it rotate? Tidal locking is expected for planets in close orbits around small stars, but some models suggest Proxima Centauri B might rotate if its orbit is not perfectly circular or if orbital dynamics have been complex. Does Proxima Centauri B have a magnetic field? A magnetic field would provide protection from stellar radiation, making habitability more likely. Magnetic fields are generated by moving liquid metal in a planet's interior. Whether Proxima Centauri B has sufficient internal heat and a liquid core to generate a magnetic field remains unknown. What is the internal structure of Proxima Centauri B? Is it similar to Earth with a rocky mantle and a liquid iron core? Or is it different, perhaps a super-Earth with a larger core and higher internal pressure? Determining the internal structure would require additional observations or modeling based on the planet's mass and potential radius measurements. Let me now discuss the detailed characteristics and properties of the three Alpha Centauri stars in much greater depth, as understanding their individual nature is crucial to understanding the system as a whole. Alpha Centauri A is a G2 type star, making it a near-perfect solar twin. It's only about 1.1 times more massive than our Sun and about 1.5 times more luminous. What's remarkable about Alpha Centauri A is how similar it is to our Sun in terms of age and evolutionary stage. Both are main sequence stars, stars fusing hydrogen in their cores. Both have entered their middle age. Our Sun is about 4.6 billion years old and has another 5 billion years of relatively stable hydrogen burning left. Alpha Centauri A is believed to be slightly older, perhaps 5 to 6 billion years old, and similarly has billions of years remaining. This similarity means that if any civilization exists around Alpha Centauri A, it emerged under conditions very similar to Earth's. The stellar energy flux, the chemical processes occurring in the star's atmosphere, the star's variability over time, all of these would be comparable to our Sun. A planet in Alpha Centauri A's habitable zone would experience seasonal variations and climate patterns not dissimilar from Earth. If life evolved there, it would have had roughly as much time as life on Earth has had, billions of years, to diversify and develop complexity. Alpha Centauri b, by contrast, is a K1 type orange dwarf. It's only about 0.9 times the Sun's mass, but crucially is only about 0.5 times the Sun's luminosity. Being less massive, Alpha Centauri b burns its hydrogen fuel more slowly than the Sun, or Alpha Centauri a. This means its main sequence lifetime is much longer, perhaps 15 billion years or more total, with about 10 billion years remaining. Alpha Centauri b is therefore significantly younger in terms of its total lifespan compared to the Sun. The slower burn rate of Alpha Centauri b's nuclear fuel has important implications. Stars that burn slowly remain relatively stable over long periods. A habitable planet around Alpha Centauri b could potentially maintain stable surface conditions for far longer than Earth has existed. If life arose around Alpha Centauri b, it would have an extraordinarily long window of habitability, not millions of years or even billions, but potentially tens of billions of years of stable conditions. This would provide ample time for life to evolve from simple chemistry to extraordinary complexity. The cooler surface temperature of Alpha Centauri b compared to Alpha Centauri a, or the Sun, also affects its habitable zone. A cooler star emits more of its energy in the infrared and less in the visible and ultraviolet. Any planets in Alpha Centauri b's habitable zone would receive more infrared radiation and less harsh ultraviolet radiation than Earth-orbiting planets. Life around Alpha Centauri b might not face the same ultraviolet damage pressures that life on Earth does. Proxima Centauri, the M5.5 type red dwarf, is the smallest and faintest of the three stars. Being only about 0.12 times the Sun's mass, Proxima Centauri produces only about 0.0017 times the Sun's luminosity, roughly 150 times dimmer than the Sun. Yet despite its incredible faintness, Proxima Centauri is not insignificant. Its small mass means it burns hydrogen extremely slowly. A red dwarf like Proxima Centauri could potentially remain in the main sequence for hundreds of billions of years, far longer than the current age of the universe. The lifetime perspective is mind-boggling. The universe is currently about 13.8 billion years old. Proxima Centauri will continue fusing hydrogen for potentially 10 trillion years or more. This means that even if the universe expands forever and stars gradually burn out over trillions of years, Proxima Centauri would be among the last stars to die. Life that evolved around Proxima Centauri, if it exists or if it evolves, would have literally trillions of years to persist, evolve, and diversify. The color of Proxima Centauri is distinctly reddish. Red dwarfs emit most of their energy in the infrared and red portions of the spectrum. To our eyes, Proxima Centauri appears as a faint reddish star. This color reflects the star's cool surface temperature, about 3,000 Kelvin compared to the Sun's 5,800 Kelvin. Now let me discuss comparative planetology, how conditions around different Alpha Centauri stars would create different planetary environments. A planet in Alpha Centauri A's habitable zone would experience similar conditions to Earth. It would receive comparable energy flux from its star. If the planet had an oxygen atmosphere like Earth's, the sky would appear similar: blue during the day from Rayleigh scattering of light, red during sunrise and sunset. The day-night cycle would be similar to Earth's if the planet has an axial tilt comparable to Earth's. A planet in Alpha Centauri b's habitable zone would experience slightly different conditions. The cooler stellar light, richer in infrared and depleted in ultraviolet, would create a different visual environment. The sky might appear more orange-red than Earth's blue. The radiation environment would be gentler. If the planet had water oceans, the water would absorb more of Alpha Centauri b's light, perhaps appearing greenish rather than Earth's blue. A planet in Proxima Centauri's habitable zone would be extraordinarily different. The immense proximity to the star, so close that the planet likely remains tidally locked, would create an extreme environment. One hemisphere would experience perpetual daylight from Proxima Centauri, creating intense heating and ultraviolet exposure. This opposite hemisphere would experience perpetual darkness, becoming desperately cold. If an atmosphere existed, wind circulation would transport heat around the planet, creating a terminator region, the boundary between day and night, where conditions might be moderate. The radiation environment would be dominated by the frequent stellar flares from Proxima Centauri. A planet around Proxima Centauri would need to either tolerate frequent radiation pulses or be well protected. Deep ocean life would be safer than surface life. Subsurface life in the crust or mantle would be protected entirely from stellar radiation. Despite these differences, one key point connects all three scenarios. Each would create a unique, potentially habitable environment. Each would present different challenges and opportunities for life. Each would shape the evolution of any organisms living there in profoundly different directions. Let me discuss observations with the future James Webb Space Telescope and beyond. The James Webb Space Telescope, launched in December 2021, has already begun observing Alpha Centauri. JWST's infrared sensitivity allows it to observe cool objects that would be invisible to earlier telescopes. JWST has observed Proxima Centauri and can potentially observe the stars in the Alpha Centauri AB system with unprecedented detail. One key capability of JWST is atmospheric spectroscopy of exoplanets. If a planet transits in front of its star, passing between us and the star's light passes through the planet's atmosphere. The atmosphere absorbs specific wavelengths of light, creating absorption features in the spectrum. By analyzing these features, astronomers can determine what gases are present in the planet's atmosphere. For Proxima Centauri b, if it transits, JWST could potentially measure whether the planet has an atmosphere and what that atmosphere contains. Detecting oxygen would be particularly significant because oxygen is produced by living organisms on Earth. Similarly, detecting methane in combination with oxygen could suggest biological activity, because these gases would quickly react with each other and disappear unless constantly replenished by life. However, there are caveats. Oxygen can be produced through non-biological processes. Methane can be produced through geological processes. No single atmospheric gas definitively proves life, but combinations of gases in certain proportions could suggest biological activity. The Nancy Grace Roman Space Telescope, scheduled to launch in the mid-2020s, will have even greater capabilities than JWST for direct imaging of exoplanets. Roman might be able to directly photograph Alpha Centauri planets, seeing them as distinct points of light rather than inferring their existence through indirect methods. Direct imaging would allow measurement of the planet's colors and potentially spectroscopy of their atmospheres if they are bright enough. Ground-based telescopes are also improving. The extremely large telescope, currently under construction in Chile, will have a primary mirror 39.3 meters in diameter, larger than any current ground-based telescope. When operational, ELT will provide unprecedented resolution and light-gathering capability.
It could potentially resolve details of Alpha Centauri planets and provide spectroscopic observations. Combining observations from JWST, Roman, ELT, and other future telescopes will create a comprehensive picture of the Alpha Centauri system far beyond what currently exists. Within the next 15 to 20 years, we might know much more about whether planets around Alpha Centauri A or B exist, what Proxima Centauri B's atmosphere contains, and perhaps even whether any biosignatures are present. Now let me discuss concepts for interstellar probes to Alpha Centauri, because understanding how we might reach the stars is important to understanding Alpha Centauri's future in human civilization. Project Breakthrough Starshot, announced in 2016 by tech entrepreneur Yuri Milner, proposes to send microscopic probes to Alpha Centauri using light sails. The concept involves a postage stamp-sized probe with a large, ultralight sail connected by thin tethers. A powerful ground-based laser array, yet to be constructed, would bombard the sail with photons. The radiation pressure from the photons would accelerate the probe. The specifications are ambitious. A gram-scale spacecraft with a multi-meter diameter sail accelerated by a
100 gigawatt laser, equivalent to the power output of a major power plant, to 20% the speed of light. Such a probe could reach Proxima Centauri in about 20 years. Once at Alpha Centauri, the probe would conduct observations, imaging the stars and planets, measuring radiation, analyzing stellar activity. It would transmit data back to Earth, but the transmission would take 4.37 years to travel the distance. So a probe arriving at Alpha Centauri in 20 years would send first images back to Earth in about 24 years, received in 2040-ish if launched around 2020. Starshot remains conceptual. No such laser array exists yet. The technological challenges are immense. But the concept is considered physically possible. No known laws of physics forbid it. It represents humanity's most concrete plan for reaching another star system. Other probe concepts have been proposed. Generation ships, enormous spacecraft carrying thousands of people, and suspended animation systems could in principle reach Alpha Centauri over centuries. Antimatter rockets could provide incredible propulsion, but we have no way to produce or store antimatter in the quantities needed. Fusion rockets represent a more realistic long-term possibility using technologies being developed for other purposes. Each concept has challenges. Starshot's challenge is building a 100 gigawatt laser and operating it with precision for years to accelerate a probe. Generation ships face biological and psychological challenges. Could people survive centuries in a confined spacecraft? Fusion rockets need efficiency improvements and testing at scales we haven't yet achieved. Yet across all these concepts runs a common theme. Alpha Centauri is close enough that reaching it is theoretically possible with advanced technology. The timescales are long, decades to centuries, but they're within the realm of technological possibility, unlike the millions of years required with conventional rockets. Let me discuss planetary magnetospheres and their importance for habitability around the Alpha Centauri stars. A planet's magnetosphere is the region of space around a planet dominated by the planet's magnetic field. Earth's magnetosphere extends roughly 60,000 kilometers from the planet's surface toward the Sun, and much farther on the night side away from the Sun. The magnetosphere protects Earth's atmosphere and surface from the solar wind, streams of charged particles constantly flowing outward from the Sun. Without Earth's magnetosphere, the solar wind would gradually strip away our atmosphere over time. Earth's magnetosphere deflects most of the solar wind particles, causing them to flow around the planet rather than striking the atmosphere. Some particles enter the magnetosphere near the poles, where the magnetic field lines converge, creating the aurora borealis and australis, the northern and southern lights. Proxima Centauri is much more active than the Sun, producing stronger and more frequent stellar winds and flares. A planet around Proxima Centauri would face a much more intense particle flux. Proxima Centauri b would need either a strong magnetosphere or a thick atmosphere to retain a volatile atmosphere over billions of years. The strength of a planet's magnetosphere depends on the planet's magnetic field, which depends on having a liquid iron core and sufficient internal heat to drive convection in that core. Large planets with massive iron cores generate stronger magnetic fields than small planets. Earth's magnetosphere is strong enough to deflect the solar wind. The Moon, lacking a liquid iron core and thus lacking a magnetic field, has no magnetosphere. Does Proxima Centauri Besa have a magnetic field? This is unknown. If it has a mass of 1.3 Earth masses and a similar composition to Earth, it might have a liquid iron core and thus a magnetic field. But if Proxima Centauri b is a water world or a super-Earth with a smaller core relative to its size, it might lack a sufficient magnetic field. Without a magnetosphere, Proxima Centauri b would struggle to retain an atmosphere against Proxima Centauri's intense stellar wind and flares. Interestingly, some models suggest that planets around active red dwarfs like Proxima Centauri could maintain atmospheres even without magnetic fields. A sufficiently thick atmosphere could provide protection from stellar winds. Additionally, if Proxima Centauri b is tidally locked and has significant atmospheric circulation, heat transport from the day side to the night side could create surprisingly complex atmospheric dynamics. The upper atmosphere might be blown off, but lower atmospheric layers could persist. Let me discuss tidal heating and its role in planetary geology. Tidal heating occurs when a celestial body is pulled gravitationally by another body in a way that deforms it. The deformation causes friction within the body, generating heat. The more intense the tidal forces, the more heat is generated. Proxima Centauri b orbits only 0.0485 astronomical units from Proxima Centauri, incredibly close. Proxima Centauri's gravity exerts enormous tidal forces on the planet, deforming it slightly as it orbits. This deformation generates heat in the planet's interior. The amount of tidal heating depends on the planet's orbital parameters and the planet's internal properties. For Proxima Centauri b, models suggest tidal heating could produce internal heat comparable to radioactive decay heating. This means Proxima Centauri b might have significant internal geological activity, volcanism, plate tectonics, mantle convection, even though it has a relatively small mass. On Earth, internal heat drives plate tectonics and maintains a magnetic field. Similarly, tidal heating on Proxima Centauri b could drive geological activity and potentially power a magnetic field through convection in the iron core. The implications for habitability are profound. Tidal heating means Proxima Centauri b could have hydrothermal vents on the seafloor if it has oceans. These vents would support deep ocean ecosystems powered by chemical energy, not sunlight. Even if the surface and upper atmosphere are rendered inhospitable by stellar flares, deep ocean life could persist, shielded by the water and the planet's crust. Conversely, if tidal heating is too intense, it could drive catastrophic volcanism, making the surface completely uninhabitable. The level of tidal heating for Proxima Centauri b likely sits somewhere between these extremes, significant enough to provide an energy source for geological processes and deep ocean life, but not so intense as to make the planet a hellscape of constant eruptions. Let me discuss the carbon cycle and climate regulation on potentially habitable planets around Alpha Centauri stars. Earth's climate is regulated by a feedback mechanism called the carbon cycle. Carbon dioxide in the atmosphere traps heat, warming the planet. Warmer temperatures increase the rate of weathering of rocks on Earth's surface. Chemical weathering removes carbon dioxide from the atmosphere, cooling the planet. If the planet cools too much, weathering slows, carbon dioxide accumulates, and the planet warms. This negative feedback has kept Earth's surface temperature habitable for billions of years, despite the sun's gradual brightening. A habitable planet around Alpha Centauri A or B would need a similar carbon cycle mechanism to maintain stable temperatures. Without such regulation, a planet could slip into a runaway greenhouse effect, becoming too hot for liquid water, or a snowball state, becoming frozen over. The carbon cycle requires geological activity, volcanism to replenish atmospheric carbon dioxide, water for weathering, and appropriate planetary parameters, appropriate size, composition, magnetic field for retaining atmosphere. A planet around Proxima Centauri faces different challenges. The intense stellar radiation and flares might drive chemical reactions in the atmosphere that would otherwise be slow. The tidally heated interior might produce abundant carbon dioxide through volcanism. An atmospheric circulation driven by extreme temperature differences between day and night sides could transport gases in unexpected ways. Whether a habitable planet around Proxima Centauri could maintain climate stability is uncertain. It might require a thicker atmosphere than Earth's to transport heat more efficiently and buffer against temperature swings. It might require different feedback mechanisms than Earth's carbon cycle. Or it might be impossible for a planet at Proxima Centauri's distance to maintain long-term climate stability, making life unlikely despite the presence of potentially habitable conditions. Let me discuss the timescales of planetary evolution around the Alpha Centauri stars. Planetary evolution occurs over billions of years. Early in a planet's history, after the formation process concludes, the planet is hot from accretional heating and radioactive decay. Impacts from large asteroids and planetesimals shape the surface. Gradually, over hundreds of millions to billions of years, the planet cools, develops a crust and mantle structure, establishes plate tectonics, if it's large enough, and becomes geologically stable enough for life. On Earth, the earliest chemical signatures of life appear in rocks about 3.8 billion years old, less than a billion years after the planet formed. This suggests that life emerged relatively quickly once conditions allowed, but complex multicellular life didn't appear until about 600 million years ago, after more than 3 billion years of single-celled life. A planet around Alpha Centauri, A or B, orbiting a star with billions of years of stability ahead, could follow a similar evolutionary path. A young planet would have a few 100 million years of heavy bombardment before settling into a more stable state suitable for life. Once stable, it would have billions of years for life to emerge and diversify. A planet around Proxima Centauri might face different constraints. The intense stellar activity in Proxima Centauri's early history, red dwarfs are typically most active when young, might have driven atmospheric loss and sterilizing radiation. A planet would need to withstand this early onslaught. If it did, it would then have the entire future lifetime of the universe to develop life, billions and trillions of years. The timescale differences have profound implications. A planet around Proxima Centauri could experience trillions of years of evolution, vastly more time than Earth has had. Life around Proxima Centauri, if it exists, could reach levels of complexity, diversity, and sophistication utterly unimaginable to us. Let me discuss the observational future of Alpha Centauri in greater detail. In the next 20 years, several key observations could dramatically expand our knowledge of Alpha Centauri. First, continued radial velocity observations of Proxima Centauri will refine knowledge of Proxima Centauri B and D, and might discover additional planets. Each new planet discovery constrains models of system formation. Second, searches for planets around Alpha Centauri A and B will continue with ever more sensitive methods. If even one planet is found around these stars, it would be a major discovery, suggesting that planets are common even in binary star systems. Third, transit observations might detect planets passing in front of their stars. If Proxima Centauri B transits, observations with JWST could reveal atmospheric composition. If planets are discovered around Alpha Centauri A or B, and they transit, similar observations could be made. Fourth, direct imaging of planets might become possible. This requires technological advances but is not ruled out by physics. Fifth, astrometric observations, measuring the positions of stars as they wobble due to planetary gravity, might reveal planets that other methods miss. Sixth, occultation observations, carefully monitoring light curves as planets pass behind or in front of stars from our perspective, could reveal planetary properties. Combining all these observations would create a comprehensive picture of the Alpha Centauri system, far beyond what currently exists. We would know how many planets orbit each star, where those planets orbit, what their sizes and masses are, potentially their compositions, potentially their atmospheric properties, and possibly whether any biosignatures are present. Let me discuss the question of whether we will ever send humans to Alpha Centauri. Sending humans to Alpha Centauri is far more difficult than sending probes. Humans need life support, food, water, air, shelter from radiation. Humans need psychological stability. Not all humans can endure years of confinement in a spacecraft. Humans need gravity, or at least some method to prevent muscle and bone loss from microgravity. A crewed spacecraft to Alpha Centauri, traveling at 20% light speed, would take 20 years to arrive. If it carried people at 20 to 30 years old at departure, they would arrive at 40 to 50 years old. This is feasible. The astronauts would survive the journey and have decades of productive life remaining to explore Alpha Centauri. But a 20-year journey requires extraordinary advances in propulsion technology. Even reaching 10% light speed might be possible within a century. Reaching 20% would require yet more advances. A timeline of a century to launch a crewed mission seems reasonable as a rough estimate. Could we do it in less? With fusion rockets or even antimatter rockets perhaps, but these technologies are far from realization. Could we not do it? Decide as a civilization that the challenge isn't worth the effort? Also possible. Perhaps in 1,000 years, humans will have moved on to other priorities, or will have reached other star systems closer by some then undiscovered warp drive. But if humans are still around in a few centuries and still motivated by exploration, Alpha Centauri will beckon. It will remain the most accessible star system. The technological challenges, while enormous, are not impossible. And the promise of meeting alien life, of discovering new worlds, of expanding human civilization beyond Earth and its immediate neighborhood is powerful motivation. Might the first humans to Alpha Centauri be biological humans like us, or artificial intelligences, or uploaded human minds in digital form? The farther we look into the future, the harder it is to predict. But one way or another, one day, perhaps within 1,000 years, perhaps in 10,000, humans or our successors might stand on the surface of a world orbiting Proxima Centauri. Let me discuss the philosophical implications of Alpha Centauri's existence and accessibility. Alpha Centauri's proximity, a mere 4.37 light-years, is both tantalizing and humbling. It's close enough that we can observe it in detail with current telescopes. It's close enough that future technology might reach it with probes within decades or humans within centuries. It's close enough to remind us that space exploration is not an indefinite frontier, but one we might actually traverse. Yet 4.37 light-years is incomprehensibly vast on human scales. Light from Alpha Centauri takes 4.37 years to reach Earth. The fastest spacecraft humans have built would take millions of years to get there. The distance simultaneously demonstrates humanity's potential and our limitations. Alpha Centauri also raises profound questions about life in the universe. If planets exist around Alpha Centauri, and we know at least some do, then planets must exist throughout the galaxy. The galaxy contains hundreds of billions of stars, potentially trillions of planets. If habitable planets are common, then life might be common. Why haven't we detected signals from alien civilizations? This is the Fermi paradox, the contradiction between the apparent probability of life and our failure to detect it. Alpha Centauri's proximity makes it the most likely place to find an answer to this paradox. If a signal from an alien civilization exists in the galaxy, perhaps one from Alpha Centauri might be detectable. If life exists somewhere, Alpha Centauri is the most accessible place to look. Let me discuss some fascinating details about the discovery history of Alpha Centauri that reveal how our understanding of this system has evolved. Ancient astronomers recognized the two bright stars in Alpha Centauri as a prominent feature in the southern sky. They appear to be one star to the naked eye, separated by about 2.2 arc seconds, roughly 1/100th the width of the moon. Ancient star catalogs listed them as separate stars only sometimes. Christian Huygens, the Dutch astronomer, made detailed observations in the 1600s and clearly identified the pair as separate stars. Subsequent observers measured their separation and positions. For a long time, it was unclear whether the two stars were actually orbiting each other or were simply close in our line of sight, but vastly different distances from Earth. The breakthrough came when astronomers measured proper motion, the apparent movement of stars across the sky over decades and centuries. Stars move through the galaxy, and this motion becomes apparent when observed over long periods. Remarkably, Alpha Centauri A and B have nearly identical proper motion, suggesting they move together through space. This was strong evidence they are physically bound by gravity, not just appearing close to us. Direct measurement of the orbital period of Alpha Centauri A and B came from observations over 2 centuries. The first position measurements from the 1700s and 1800s, combined with modern measurements, revealed the orbital motion. The orbital period of 79.9 years matches prediction from their masses and separation, confirming they orbit each other. The discovery of Proxima Centauri in 1915 was initially controversial. Robert Innes's detection of this faint red dwarf was based on photographic plates, long exposure images on photographic film. Other astronomers had to confirm that Proxima was indeed a star and not a photographic artifact or asteroid. Once confirmed, its proximity to Alpha Centauri A and B suggested a physical triple system. Proving that Proxima is actually bound to Alpha Centauri required measurements of its proper motion and velocity. If Proxima moved at the same velocity as Alpha Centauri A and B, it was likely bound. Modern measurements confirm this. Proxima Centauri moves with Alpha Centauri A and B through space, despite being far from them, bound by their collective gravity. Understanding the orbital period of Proxima Centauri around the Alpha Centauri AB system took longer because the period is millions of years, far longer than human observation timescales. The current best estimate suggests Proxima takes about 730,000 years to orbit the center of mass of the Alpha Centauri AB system. Let me discuss the implications of finding life in the Alpha Centauri system because this is perhaps the most consequential possible discovery. If robotic probes or future observations discovered microbial life on Proxima Centauri B or around Alpha Centauri A or B, this would be perhaps the most profound discovery in human history. Why? Because it would answer one of humanity's deepest questions. Are we alone? Currently, we have only one example of a planetary biosphere, Earth. We cannot say whether life is common or rare, whether it emerges readily or requires extraordinary circumstances. The discovery of even one example of extraterrestrial life would expand our sample size enormously. If life around Alpha Centauri shares a genetic basis with Earth life, using DNA or something similar, it would suggest that life's chemistry is fundamentally similar throughout the universe. This would support the idea that life emerges wherever conditions allow. If life around Alpha Centauri is completely different, using silicon instead of carbon or some novel biochemistry we haven't imagined, it would suggest life is even more diverse and more likely than we assumed. It would demonstrate that life's chemistry is more flexible than terrestrial biology suggests. Either way, the existence of even one other biosphere would transform our understanding of life's place in the cosmos. It would suggest that the galaxy might contain billions of biospheres. It would raise the question of why we haven't detected civilizations. It would inspire new searches for life throughout the galaxy and beyond. Furthermore, studying extraterrestrial life would revolutionize biology. We would understand how life really works at its most fundamental level, not just how Earth life works. We would learn which principles are universal and which are contingent on Earth's particular conditions. The implications for medicine, biotechnology, and our understanding of evolution would be extraordinary. The discovery of intelligent life in the Alpha Centauri system would be even more profound. It would tell us that intelligence emerges commonly around stars. It would provide examples of alternative evolutionary paths that produce intelligence. It would potentially allow communication with another civilization. The philosophical implications would be staggering. Humanity would no longer be the only known intelligence in the universe. We would be one among many. Our civilization would take its place in a larger cosmic community. Let me discuss the role of Alpha Centauri in long-term human civilization and space expansion. If humanity survives and develops advanced technology over the coming centuries and millennia, space exploration will expand. First Mars, then other planets and moons in the solar system. Eventually, perhaps, other stars. Alpha Centauri would likely be the first target for crewed interstellar missions. The star system's proximity makes it the most accessible. Any technological achievements that allow reaching Alpha Centauri could also be applied to nearer targets, but would be wasted on much farther targets. A human civilization that reaches Alpha Centauri would have transformed itself in the process. The technology required, propulsion systems capable of reaching a significant fraction of light speed, life support systems functional for decades, radiation shielding, psychological support, systems for long voyages would be far beyond current capabilities. The astronauts would be highly trained, possibly augmented with biological enhancements or cybernetics to survive the journey and radiation exposure. Once at Alpha Centauri, establishing human settlements would require terraforming technology, with the ability to modify a planet's climate and atmosphere to support human habitation. Or settlements might be built in artificial habitats, domed cities, space stations, rotating habitats providing artificial gravity. Over thousands of years, human civilization might spread throughout the Alpha Centauri system. Populations would adapt to local conditions. Isolated populations would evolve differently. The Alpha Centauri system might become as familiar to future humanity as Earth is to us, a center of civilization and culture. Alpha Centauri might not be the only star system inhabited by humans or their descendants. If reaching Alpha Centauri is achievable, reaching other stars eventually becomes achievable with enough technological progress. Over millions of years, humanity might spread throughout the galaxy, becoming a galactic civilization. The timeline for such expansion is highly speculative. It could take centuries, millennia, or prove impossible and never occur. But from the perspective of physical possibility, humanity reaching Alpha Centauri and establishing a presence there is possible with sufficiently advanced technology. Let me discuss what observations we can make of Alpha Centauri from the southern hemisphere with current telescopes. For those of us in the northern hemisphere, Alpha Centauri is inaccessible. It never rises above the horizon. But from the southern hemisphere, particularly from southern locations like Australia, South Africa, or southern Chile, Alpha Centauri is prominent in the southern sky. Alpha Centauri A and B appear as a single star to the naked eye, yellowish in color, one of the brightest stars in the southern sky. With binoculars, the two components separate. With a small telescope, they appear as two distinct stars, clearly separated. Proxima Centauri, by contrast, is invisible to the naked eye, even from ideal locations with dark skies. It requires a telescope to see. It appears as a faint reddish star, barely distinguishable from background stars without careful observation. Amateur astronomers in the southern hemisphere can observe Alpha Centauri and track the orbital motion of the two bright components. Over months and years of observations, the changing separation and angle between Alpha Centauri A and B become apparent. Professional observatories in the southern hemisphere, in Chile, South Africa, and Australia, conduct detailed observations of Alpha Centauri. Spectroscopic observations reveal the composition and motion of the stars. Observations at infrared wavelengths detect the heat from the stars. Photometry measures the brightness and searches for the tiny dimming that would occur if a planet transited in front of a star. Space-based telescopes like JWST observe Alpha Centauri regardless of location. JWST can observe in infrared wavelengths at a level of detail impossible from the ground, even in dark locations away from atmospheric disturbance. The combination of ground-based and space-based observations creates a comprehensive picture of the Alpha Centauri system far beyond what any single observatory could achieve. Let me discuss the concept of biosignatures and how astronomers might detect life in the Alpha Centauri system. A biosignature is a chemical sign of life. On Earth, life produces particular gases and chemical abundances that are unusual in chemical disequilibrium in ways that wouldn't occur naturally without life. For instance, Earth's atmosphere contains oxygen, about 21%. Oxygen is reactive and combines with other elements fairly quickly. Without biological production of oxygen through photosynthesis, Earth's atmosphere would contain almost no free oxygen. The presence of oxygen is a biosignature because it indicates biological oxygen production. Earth's atmosphere also contains methane. Methane is produced both biologically and geologically, but the proportion of methane in Earth's atmosphere is higher than would occur from geological processes alone. The combination of oxygen and methane in Earth's atmosphere is a strong biosignature, unlikely to occur without life. If an exoplanet's atmosphere contains similar biosignatures, astronomers would have evidence of life. However, detecting atmospheric composition requires special circumstances. The planet must transit in front of its star from Earth's perspective, allowing starlight to pass through the atmosphere. Sensitive spectroscopy can then detect absorption by atmospheric gases. For Proxima Centauri b, if it passes in front of Proxima Centauri, JWST might detect its atmospheric composition. If the atmosphere contains unexpected abundances of oxygen, methane, or other biomarkers, this would suggest life. However, there are caveats. False positives could occur. abiotic processes that produce oxygen or methane. And if Proxima Centauri b lacks an atmosphere, or if its atmosphere is too thick to analyze, spectroscopy would reveal nothing about any life on the planet. Despite these limitations, the search for biosignatures in exoplanet atmospheres represents humanity's best current strategy for detecting extraterrestrial microbial life. Alpha Centauri, with its nearby planets and our ability to observe them with increasingly powerful telescopes, will be a prime target for this search. Now, let me conclude with deeper reflection on what Alpha Centauri means for humanity. Now, let me reflect on what Alpha Centauri means to humanity and our future. Alpha Centauri represents the frontier of human exploration. It is the nearest star system we might eventually reach. It represents a challenge that humanity might work toward over centuries or millennia. It embodies the human drive to explore, to reach beyond current limits, to venture into the unknown. Alpha Centauri is also a reminder of human insignificance. The distance to Alpha Centauri is so vast that even our most ambitious plans for space exploration would require technology far beyond what currently exists. It would take generations of development, vast resources, and sustained commitment to mount a mission to Alpha Centauri. Yet we are compelled to try, compelled to reach beyond, compelled to explore. The search for life in the Alpha Centauri system touches on fundamental questions about life in the universe. Are we alone? Is life common or rare? If life is common, why haven't we detected it yet? If life is rare, does that make humanity's existence more or less significant? Alpha Centauri also represents a connection between Earth and the wider cosmos. The light we see from Alpha Centauri has traveled 4.37 years through space to reach our eyes. That light carries information about stars and planets and the processes occurring there. By studying this light, we connect ourselves to Alpha Centauri across the vast gulf of space. The atoms that make up the Alpha Centauri stars were forged in previous stars in supernova explosions. The atoms that make up any planets around Alpha Centauri were formed through similar processes. The atoms that make up human bodies were forged in stars. In a very real sense, we share a common origin with Alpha Centauri. We are all made of star stuff. Let me discuss the comparative habitability of planets in different parts of the Alpha Centauri system. Proxima Centauri b orbits very close to its star, receiving intense radiation. If the planet is tidally locked, one hemisphere is always facing the star and always in daylight, while the other hemisphere is always in darkness. The day side would be extremely hot, the night side extremely cold. This would create a very different environment than Earth. Some models suggest that a tidally locked planet with an atmosphere could circulate heat from the day side to the night side, creating an equilibrium temperature that makes habitability possible. Such a world might have a region at the terminator, the boundary between day and night, where temperatures would be moderate. Life on such a world would need to adapt to extreme conditions, to either the heat of the day side or the cold of the night side, or to the particular conditions at the terminator. A hypothetical planet in the habitable zone of Alpha Centauri A or B would be more similar to Earth. The planet would receive roughly Earth-like radiation levels. If it had a day-night cycle and moderate temperatures, it might host Earth-like conditions and life. The timescales for planetary evolution differ for the different Alpha Centauri stars. Alpha Centauri A will remain in the main sequence for about 5 to 6 billion years more. Alpha Centauri B will remain in the main sequence for 15 plus billion years. Proxima Centauri could remain in the main sequence for trillions of years. A planet orbiting Alpha Centauri has a limited time window for life to evolve and flourish before the star expands into a red giant and incinerate nearby planets. Planets around Alpha Centauri b or Proxima Centauri could harbor life for vastly longer periods, potentially for the entire future lifetime of the universe, assuming the universe doesn't collapse or undergo some other catastrophic change. Let me discuss observations of Alpha Centauri with different types of telescopes. Visible light observations show Alpha Centauri as two bright stars from the southern hemisphere and Proxima Centauri as a very faint star. Detailed imagery shows the spiral structure if planets transit in front of the stars. Infrared observations reveal the heat emitted by the stars. All stars emit heat in the infrared as a consequence of their surface temperature. The stars' infrared spectra reveal information about their composition and temperature. Ultraviolet observations reveal high-energy phenomena in the stars' atmospheres. Proxima Centauri is particularly active in the ultraviolet, producing intense ultraviolet radiation during stellar flares. Radio observations can reveal activity in the stars' atmospheres and the presence of stellar magnetic fields. Some stars produce radio emissions from their magnetospheres. X-ray observations reveal the most energetic processes in the stars' atmospheres, particularly stellar flares and coronal heating. Proxima Centauri produces X-rays, particularly during stellar flares. Each type of observation provides different information about the Alpha Centauri stars. Combining observations across the electromagnetic spectrum creates a comprehensive picture. Now let me discuss the role of Alpha Centauri in human culture and imagination. Alpha Centauri has featured prominently in science fiction. Numerous science fiction stories feature human space travelers visiting Alpha Centauri. Some feature interstellar civilizations already established there. Others feature humans discovering life or ruins of ancient civilizations. These stories explore themes of exploration, the search for life, and humanity's future among the stars. Alpha Centauri also features in popular culture, in books, movies, video games, and other media. It often represents the frontier of human expansion, the next great challenge after Earth and the solar system. The real Alpha Centauri, observed by astronomers, is far from the fictional versions. It's a triple star system with planets we can barely detect, orbiting at distances we can barely fathom. Yet the reality is no less fascinating than the fiction. The possibility that habitable planets might exist in the Alpha Centauri system captures the imagination just as powerfully as any fictional scenario. Let me now discuss what future observation might reveal about Alpha Centauri. Improved spectroscopy could reveal the atmospheric composition of exoplanets around Alpha Centauri. By analyzing how light from the Alpha Centauri stars is filtered by planetary atmospheres, astronomers could determine what gases are present. If an atmosphere contains oxygen or other biosignatures, this would suggest the presence of life. Direct imaging of exoplanets around Alpha Centauri could eventually become possible with future large telescopes. Directly seeing the planet would provide far more information than indirect detection methods. Occultation observations, where a planet passes in front of its star and briefly dims its light, could reveal planetary sizes and, potentially, atmospheric properties. Alpha Centauri planets might eventually be observed in such occultations. Gravitational microlensing or other advanced techniques might reveal planets that remain hidden to current methods. Each new observation method potentially reveals previously undetected planets. The observation of Alpha Centauri will continue for as long as human astronomy continues. Each new generation of telescopes will reveal more details about this nearest star system. Each new discovery will refine our understanding and raise new questions. Let me reflect on why Alpha Centauri matters for science and human destiny. Alpha Centauri is the nearest star system. For this reason alone, it matters. It represents the closest frontier of human exploration. Any civilization advancing beyond its home star system would most likely venture first to the nearest stars. Alpha Centauri might harbor life. The presence of potentially habitable planets around Proxima Centauri makes this a compelling target for the search for extraterrestrial life. If life is discovered in the Alpha Centauri system, it would answer one of humanity's most profound questions. Are we alone in the universe? Alpha Centauri demonstrates the possibility of planetary systems. It shows that planets exist around other stars and potentially in habitable configurations. The discovery of planets in the Alpha Centauri system has implications for understanding how common planets are and how common habitable planets might be. Alpha Centauri connects us to the broader cosmos. By studying Alpha Centauri, we study stellar physics, planetary science, and the conditions necessary for life. This knowledge applies not just to Alpha Centauri, but to all stars and all planets throughout the universe. Understanding Alpha Centauri is understanding the context in which Earth exists. Earth is one planet, orbiting one star in one system. But Earth's system is part of a larger structure, a galaxy containing billions of stars and potentially trillions of planets. Studying our nearest neighbors helps us understand our place in this vast structure. Now let me address the ultimate question about Alpha Centauri. Could humans ever travel there? With current technology, human travel to Alpha Centauri is impossible. The distances are too vast, the travel times too long, the technological challenges too severe. But technology advances. Humans have traveled to the moon, 250,000 kilometers away, in less than a decade after developing the technology to do so. Humans have built spacecraft that have traveled billions of kilometers to the outer solar system. Each advance in technology opens new possibilities. Conceivably, future advanced civilizations might solve the problems of traveling to Alpha Centauri. Perhaps in centuries, perhaps in millennia, human spacecraft might reach Alpha Centauri. The astronauts who arrive would be vastly different from us. Their biology modified, their minds augmented, their entire existence devoted to the mission. More realistically, the first explorers to reach Alpha Centauri might not be biological humans at all, but artificial intelligences, robots or digital minds traveling at near-light speeds with far less need for life support than biological organisms. Or perhaps humans will never reach Alpha Centauri. Perhaps the stars will remain forever distant, explored only through observation from Earth and robotic probes. This is also possible, even likely on the timescales of human civilization as it currently exists. Yet the possibility alone, the knowledge that another star system exists nearby, with potentially habitable planets, with the possibility of life, this possibility drives human imagination and scientific curiosity. As long as humans wonder about what lies beyond, as long as we are compelled to explore and understand, Alpha Centauri will call to us. Now, as I conclude, let me reflect on what Alpha Centauri truly represents for humanity and our cosmic future. Alpha Centauri is our nearest stellar neighbor, a triple star system of profound significance, home to planets including at least one potentially habitable world, and the closest target for human space exploration beyond the solar system. It represents the frontier of human ambition, the challenge that future generations might work toward, the threshold between our current era of planetary confinement and a potential era of interstellar civilization. The light we see from Alpha Centauri has traveled 4.37 light years through the void of space. This light began its journey 4 1/3 years ago, when President Barack Obama was still in office, when the world was dealing with a different set of challenges than we face today. That light has crossed the cosmic gulf between stars, passed through clouds of dust and gas, and finally reached Earth. It enters our eyes and triggers the neural signals we interpret as vision. That light carries literal information about distant stars and planets encoded in its wavelengths. When you observe Alpha Centauri, you're not just seeing a distant object. You're receiving photons that have traveled across incomprehensible distances. In the most literal sense, you are collecting particles of light that originated at Alpha Centauri. The universe has connected itself across the vast gulf between stars in a way that allows parts of itself to contemplate other parts. You are touching Alpha Centauri across the cosmic distance. The atoms comprising the Alpha Centauri stars were forged in the cores of massive stars billions of years ago, then dispersed into space by supernova explosions. The atoms making up any planets in the Alpha Centauri system originated in stars. The atoms making up your body, the calcium in your bones, the iron in your blood, the carbon and oxygen in every molecule, originated in stars and were scattered into space by stellar explosions. We are quite literally made of star stuff. When we study Alpha Centauri, when we contemplate that distant star system, the universe is studying itself. Consciousness has emerged from the cosmos and turned its gaze back upon itself. If life exists in the Alpha Centauri system, it would represent a profound discovery. If that life is based on similar chemistry to Earth's life, it would suggest life's chemistry is universal. If it's based on entirely different principles, it would suggest even greater diversity and opportunity for life throughout the cosmos. Finding life anywhere else would answer humanity's deepest question. Are we alone? Even if no life exists at Alpha Centauri, the system represents an extraordinary laboratory for understanding stars, planets, and the physical processes governing the universe. It's a frontier for human knowledge and exploration. Alpha Centauri reminds us of an unsettling cosmic fact. Earth is one world among countless billions. Our sun is one star among hundreds of billions in our galaxy alone. Our galaxy is one among hundreds of billions in the observable universe. Our civilization, our history, our individual lives are incomprehensibly small against these cosmic scales. Yet this perspective, while humbling, is also liberating. It suggests the problems we face on Earth, important as they seem, are ultimately small in cosmic context. It suggests we are capable of far more than we typically imagine. It suggests our future might extend far beyond our planet, far into the cosmos itself. Alpha Centauri specifically represents this potential. It's the nearest stepping stone in humanity's potential expansion through space. It's achievable with technology that doesn't violate known physics. A civilization that survives and thrives for centuries might reach Alpha Centauri. The system might become familiar to our descendants, as accessible as distant continents are to us today. Or perhaps we'll never reach Alpha Centauri. Perhaps we'll destroy ourselves before developing the capability. Perhaps we'll lose interest in space exploration. Perhaps we'll be replaced by successors. These are all possibilities. But Alpha Centauri is there, waiting, accessible to our observation and potentially to our exploration. The question isn't whether Alpha Centauri will be there. It has existed for billions of years and will exist for billions more regardless of our actions. The question is whether humanity will be ambitious enough, wise enough, and successful enough to reach for the stars. Alpha Centauri has been 4.37 light years away since long before humans evolved. It will remain at that distance long after human civilization ends, unless we find a way to reach it. The stars will outlast us. The cosmos is indifferent to human ambition, yet within that indifference lies possibility. The cosmos is not infinite in ways that prevent reaching it. With sufficient technology and determination, it might be touched. That is what Alpha Centauri represents. A possibility open to us, a future we might choose to pursue, a destination written in the stars themselves. Let me discuss what makes Alpha Centauri unique compared to other nearby star systems, and why it holds special significance for astronomy and space exploration. The solar neighborhood, stars within about 50 light years of Earth, contains several hundred known stars. Most are small red dwarfs like Proxima Centauri. A few are larger, brighter stars like Alpha Centauri A. Alpha Centauri AB itself represents the bright, visible frontier of nearby stars. These are the stars we can see with the naked eye from the southern hemisphere. These are the stars we can study in detail with current telescopes. Beyond the solar neighborhood, at greater distances, lie more stars. Sirius, about 8.6 light years away, is the brightest star in Earth's sky, but it's too far for crewed missions in any foreseeable time frame. The Pleiades cluster, visible as a fuzzy patch to the naked eye, consists of hundreds of stars, but they're all 400 plus light years away, vastly more distant than Alpha Centauri. Alpha Centauri's unique position as the closest star system creates special significance. It's close enough that our most sensitive instruments can study it in detail. It's far enough that it requires genuinely advanced technology to reach, providing a challenge worthy of humanity's technological ambitions. It's not trivial to study or reach, but it's not impossible either. Furthermore, Alpha Centauri contains multiple stars, a binary system with a third distant companion. This makes it a natural laboratory for understanding binary star systems, planetary formation in such systems, and the dynamics of multiple stars orbiting their common center of mass. Many of the galaxy's stars are part of multiple star systems. Learning about planets and habitability around Alpha Centauri's stars teaches us about the potential for life throughout the galaxy in similar systems. The presence of Proxima Centauri b, a potentially habitable planet in the closest star system, creates an unusual situation. Typically, the closest exoplanet to Earth is the one we observe most easily and study in greatest detail. But Proxima Centauri b is not just close, it's potentially habitable. It orbits in the habitable zone of its star. It's the closest known potentially habitable world besides Earth. This combination of factors, proximity, habitability, multiple stars, accessibility to current and future observation technology, gives Alpha Centauri an outsized importance in astronomy and space exploration. It's not just another star system. It's the star system of greatest immediate interest to humanity, the one most likely to be visited by robotic probes in the coming decades, or crewed missions in the coming centuries. The study of Alpha Centauri also serves as a proving ground for exoplanet detection technology. Methods developed to detect planets around Alpha Centauri can be applied to other nearby stars. Observations of Alpha Centauri provide practice for future observations of more distant, more challenging star systems. In this sense, Alpha Centauri is not just a destination for study, it's the training ground for the technology that will study countless other worlds.
Let me discuss stellar evolution and what the future holds for the Alpha Centauri stars. Let me discuss stellar evolution and what the future holds for the Alpha Centauri stars. Stars don't remain constant throughout their lifetimes. They slowly evolve, gradually changing composition, temperature, and luminosity. The life cycle of a star depends on its mass. Massive stars live fast and die young, exhausting their fuel in millions of years. Small stars like Proxima Centauri live slow and long, potentially persisting for trillions of years. Alpha Centauri A is currently a main sequence star in its middle age, stable, fusing hydrogen. Over the next 5 to 6 billion years, it will gradually brighten. Eventually, after billions of years, it will exhaust the hydrogen in its core and begin fusing helium. This will cause the star to expand dramatically, becoming a red giant. The star's radius might expand to encompass the inner regions of its planetary system. Any close planets would be incinerated. Alpha Centauri B will remain in the main sequence much longer, perhaps 10 plus billion years more. When it eventually becomes a red giant, it will also expand, potentially engulfing close planets. Proxima Centauri will remain a main sequence star for trillions of years. Its evolution toward red giant status is so far in the future that it's essentially irrelevant to any discussion of timescales we might care about. These evolutionary timescales matter for habitability. A habitable planet around Alpha Centauri A has only a few billion years of stable conditions before the star's evolution makes the system uninhabitable. A habitable planet around Alpha Centauri B has tens of billions of years. A habitable planet around Proxima Centauri has trillions of years, longer than the current age of the universe by an order of magnitude. For any life that might exist around Alpha Centauri, these timescales constrain the maximum age that a biosphere could reach. Life around Alpha Centauri here, A, has a deadline: the star's evolution. Life around Proxima Centauri
Faces no such deadline. The star will remain stable essentially forever, or until the universe itself ends in a heat death billions of trillions of years in the future. Let me discuss the spectroscopy of the Alpha Centauri stars and what it reveals. Spectroscopy is the art and science of analyzing light by splitting it into its component wavelengths. When light from a star is split through a prism or grating, it creates a spectrum, a rainbow of light showing all the wavelengths present. The spectrum contains absorption lines, dark lines at specific wavelengths where atoms and molecules in the star's atmosphere absorb photons. Each element absorbs light at characteristic wavelengths. Hydrogen absorbs at certain wavelengths, helium at others, calcium at still others. By analyzing which absorption lines are present, astronomers determine the star's composition. Alpha Centauri A's spectrum shows it contains the expected heavy elements: carbon, nitrogen, oxygen, iron, in abundances similar to the Sun. This confirms Alpha Centauri A is indeed a solar twin, with similar composition. Alpha Centauri B's spectrum shows it also contains heavy elements, though in different proportions than the Sun. The spectrum is consistent with a K-class star, cooler and smaller than the Sun. Proxima Centauri's spectrum shows the characteristic absorption lines of a low-mass red dwarf. Particularly prominent are lines from hydrogen, the dominant fuel in all stars. The spectrum also shows evidence of magnetic activity, broadened absorption lines that indicate the star's magnetic field is stirring up turbulence in its atmosphere. Spectroscopy also reveals stellar motion. The Doppler effect causes spectral lines to shift toward blue if the star is moving toward us, or toward red if moving away. By measuring the exact wavelength of spectral lines, astronomers can determine how fast the star is moving toward or away from Earth along the line of sight. This is how the radial velocity method detects planets. The planet's gravity causes the star to wobble, and this wobble is detected through spectral line shifts. Let me discuss the Alpha Centauri system in the context of the broader Milky Way galaxy. The Milky Way is a spiral galaxy containing about 100 to 400 billion stars. Estimates vary. Most stars in the galaxy never leave their birth region. They form in a molecular cloud, spend their main sequence lifetime within a few hundred light years of their birthplace, and eventually die. Some stars move significantly through the galaxy. The Alpha Centauri system is one such star. Measurements of its proper motion show it's moving through space at about 3.71 kilometers per second relative to the Sun. At this velocity, Alpha Centauri traverses about 1 light year every 800 years. The current position of Alpha Centauri, 4.37 light years from Earth, is part of a particular moment in time. In the past, Alpha Centauri was farther away. In the future, it will move still farther. About 26,700 years from now, Alpha Centauri will reach its closest approach to Earth, about 3.26 light years away. After that, it will gradually move farther away, becoming ever more distant and faint. This dynamic perspective is important. The Alpha Centauri system is not fixed in space. It moves through the galaxy with billions of other stars, all orbiting around the galactic center. The entire galaxy rotates. Alpha Centauri, the solar system, and all other stars orbit around the galactic core once every 225 to 250 million years, a period sometimes called a galactic year. In this larger context, the Alpha Centauri system is not special. It's one star system among billions. Yet, from our perspective, from Earth's vantage point at this particular moment in cosmic history, Alpha Centauri is special. It's the closest star to us besides the Sun. This accident of proximity makes it our natural first target for space exploration. Let me discuss what we might learn about planetary system architecture from Alpha Centauri. Alpha Centauri is a binary star system, and this environment differs significantly from our solar system, where only one star provides gravity. The presence of two stars shapes planetary system formation and architecture. In binary star systems, planets can orbit one star, circumprimary orbits, both stars, circumbinary orbits, or at large distances in wide orbits around the system's center of mass, hierarchical orbits. Each orbital configuration faces different challenges. Proxima Centauri planets orbit the star in relatively simple geometries. Proxima Centauri orbits at close distances. The Alpha Centauri AB system's potential planets, if they exist, would face perturbations from the companion star, constraining their possible orbital locations. The existence of planets around Alpha Centauri A or B would tell us that planets can form and persist in binary star systems despite the additional gravitational complexity. This expands our understanding of where planets can exist. If planets are found in a wide range of binary configurations, this suggests planets are remarkably common and can exist almost anywhere. By contrast, if planets are found only in very tight orbits around one star in the Alpha Centauri system and not in intermediate orbits, this would constrain models of planetary formation and dynamical stability in binary systems. Each new planet discovery or non-discovery in the Alpha Centauri system tests theoretical models and expands our knowledge of planetary system formation. Let me discuss the role of massive observation campaigns in studying Alpha Centauri. Astronomy is increasingly conducted through large, coordinated campaigns involving multiple telescopes and observatories worldwide. The Alpha Centauri system benefits from this approach. Radial velocity measurements require sensitive spectrographs, instruments that measure the Doppler shift in starlight with extraordinary precision. The HARP spectrograph used to discover Proxima Centauri b is one of the world's most sensitive. It's located at the European Southern Observatory in Chile and is used regularly for observations of nearby stars. Photometric observations monitoring the brightness of Alpha Centauri stars for planetary transits involve dedicated telescopes and often volunteer citizen scientists with private telescopes. Networks of amateur astronomers contribute valuable observations. Infrared observations from JWST provide data unattainable from ground-based telescopes. These observations are precious. JWST observation time is extremely limited and highly competed for. Ultraviolet observations reveal high-energy phenomena around the stars. Spacecraft carrying ultraviolet instruments provide these observations. X-ray observations reveal the most energetic processes. X-ray spacecraft and observatories conduct these observations. Radio observations detect the radio emissions from stellar activity. Radio telescopes worldwide contribute. Combining data from all these sources creates a comprehensive picture of Alpha Centauris across the electromagnetic spectrum. No single telescope could do this alone. The Alpha Centauri system's prominence in astronomy results partly from its proximity, but also from the coordinated effort of astronomers worldwide using every available tool. Let me discuss what would happen if humans actually reached Alpha Centauri and established a settlement there, as a thought experiment about humanity's future among the stars. Imagine it's the year 2250, and humanity has finally developed the technology to send a crewed mission to Alpha Centauri. The spacecraft, crewed by 500 people selected for their scientific expertise, psychological resilience, and adaptability, departs from Earth. Over the following 20 to 30 years, as the spacecraft approaches Alpha Centauri at 10 to 15% the speed of light, the crew prepares for arrival in one of humanity's most distant outposts. As the spacecraft approaches Proxima Centauri, the crew begins intensive study of the system. Proxima Centauri appears dramatically closer than from Earth, no longer just another faint star, but a genuine presence in the sky. Spectroscopic analysis reveals details invisible from Earth. Probes deployed ahead of the spacecraft conduct close reconnaissance of Proxima Centauri b and other system bodies. Assuming Proxima Centauri b is indeed habitable, or at least suitable for human settlement, the crew faces a decision: establish a surface settlement on the planet or construct orbital habitats around the star system. A surface settlement would offer gravity. People could walk around naturally without the health complications of microgravity. The planet's day-night cycle, if it exists, would be familiar. But Proxima Centauri b's stellar activity poses risks. Stellar flares bombard the surface with radiation. The environment is alien and potentially hostile. An orbital habitat offers safety. Above the planet, in space, a rotating habitat could provide artificial gravity. Radiation shielding would be more straightforward in space than dealing with the planet's flares. But there would be no solid ground beneath colonists' feet, a psychological challenge even for people who've trained extensively. Most likely, a first settlement would be orbital, perhaps a large rotating space station in orbit around Proxima Centauri b or Proxima Centauri itself. From there, exploration of the system could proceed. Eventually, if the surface proves habitable, settlements might expand to the planet. What would life be like for the colonists? They would be 4.37 light years from Earth. Communication would take 4.37 years each way. Messages from Earth would arrive ancient history. A message sent when a colonist was a child might reach them as an adult with years of intervening events to discuss. The colonists would be effectively isolated, autonomous, developing their own culture and social norms. The colony would require near complete self-sufficiency. They would need to extract resources from the local environment. They would need to repair equipment using local materials. They would need to develop food production systems, water purification, medical technology, manufacturing, all the capabilities of civilization, but adapted to the Alpha Centauri environment. Over generations, the colonists would adapt. Their children, born at Alpha Centauri, would be the first humans to grow up in a different star system's gravity and radiation environment. Their genetics might adapt over generations to the new conditions. Their culture would develop independently from Earth's, creating a distinct human civilization orbiting Proxima Centauri. Eventually, if the colony thrived, it might launch its own probe or crewed mission to other nearby stars. Alpha Centauri would become a hub of human civilization, with outposts spreading to other star systems. This is how human civilization might ultimately expand throughout the galaxy, not in great leaps, but in gradual steps from star to star. Or the colony might fail. Equipment might malfunction beyond repair. People might die faster than new people are born. Morale might collapse. Disease might devastate the population. These risks are real for any distant colony. Many Earth colonizations failed before succeeding, but if the colony succeeded, it would represent a permanent expansion of human civilization beyond Earth. Humans would no longer be confined to one star system. We would have joined other species throughout the galaxy as inhabitants of multiple worlds. This thought experiment reminds us that Alpha Centauri is not just a scientific curiosity or a distant destination for study. It's a potential home for human civilization. It's a place where humans might live, build communities, raise families, create cultures distinct from Earth's. It's a threshold to a future of spacefaring civilization. Let me expand the conclusion with deeper reflections on what Alpha Centauri means. Let me discuss what we might discover about Alpha Centauri in the next century of observations and how our understanding might evolve. In the next 10 years, radical improvements in exoplanet detection technology will likely reveal new planets in the Alpha Centauri system. The JWST observations will provide unprecedented detail about existing planets. New ground-based telescope projects, including the Extremely Large Telescope and similar facilities, will begin operations. Each new observatory will add layers of detail to our knowledge. Within 20 years, we might have detailed atmospheric observations of Proxima Centauri b. If the planet has an atmosphere, spectroscopy might reveal its composition. We might detect water vapor, carbon dioxide, methane, or other atmospheric components. This would revolutionize our understanding of the planet's habitability and suitability for life. Within 50 years, technological advances we can barely predict might make possible observations unimaginable today. Telescopes significantly larger than current ones might exist. They might achieve direct imaging of planets around Alpha Centauri A or B. They might resolve surface features on Proxima Centauri b. They might detect biosignatures, chemical signs of life, in exoplanet atmospheres. Within 100 years, human civilization might have changed so radically that comparing it to the present is impossible. Artificial intelligence might be conducting astronomical observations. Humans might be augmented with biological or technological enhancements. Space-based telescopes might be deployed throughout the solar system and beyond. The technology for detecting life signatures in exoplanet atmospheres might be routine. If a civilization persists for centuries of increasingly sophisticated observations, what might we learn about Alpha Centauri? We might discover dozens of planets in the system, in orbits we never suspected. We might map the atmospheres of multiple worlds. We might detect industrial pollution, signatures of alien civilization in planetary atmospheres. We might receive intentional signals from advanced civilizations orbiting Alpha Centauri. Alternatively, we might continue finding a seemingly barren system. Planets might orbit Alpha Centauri, but lack atmospheres or show no signs of life. The habitable zones might support only microbial life, leaving no detectable biosignatures. Advanced civilizations, if they exist, might be beyond Alpha Centauri at greater distances. Or, and this is a possibility that deserves consideration, we might discover that Alpha Centauri was once inhabited but is now empty. The ruins of an ancient civilization might exist on a planet's surface, evidence of intelligences that rose, built civilizations, and fell or left for other worlds. We might discover a graveyard of dead worlds, fossils of ancient biospheres no longer living. The implications would be profound. Discovery of any evidence of past or present life would revolutionize our understanding of life's prevalence. Discovery of an ancient extinct civilization would raise questions. Why did they disappear? Where did they go? Should we fear meeting their fate? Should we study their ruins to learn how to avoid their mistakes? These scenarios represent only a few possibilities among countless others we haven't imagined. The universe often surprises us. What we discover about Alpha Centauri, if we pursue the observations rigorously for the coming centuries, might exceed our current imaginations. But the pursuit itself is important. The act of studying the closest stars, asking questions about potential life and habitability, developing technology to observe distant worlds, and working to understand our place in the cosmos. This pursuit defines humanity at its best. It pushes us to grow, to learn, to expand our understanding and our capabilities. Alpha Centauri represents both a destination and a process. The destination is reaching the star system, establishing settlements, exploring and understanding its worlds. But the process, the centuries of observation, the development of technology, the collaboration of astronomers and engineers worldwide, the gradual expansion of human knowledge and capability. This process is equally significant. Whether or not humans ever set foot on a world orbiting Proxima Centauri, the pursuit of that goal transforms us. It inspires scientific advancement. It drives technological development. It connects humans across continents and centuries in common purpose. It reminds us that we are part of something larger than ourselves, participants in the long, ongoing human endeavor to understand our universe. Let me add one more perspective on Alpha Centauri before we conclude: the concept of cosmic perspective and what it means for human consciousness. Carl Sagan famously spoke of the pale blue dot, the tiny photograph of Earth taken by the Voyager, one spacecraft from 6 billion kilometers away. In that image, Earth appears as an almost invisible speck, smaller than a pixel. Sagan wrote about how that image, that perspective on our own world, should change how we see ourselves. Alpha Centauri offers a similar perspective but magnified. Proxima Centauri is 4.37 light years away. From there, Earth would be invisible, lost among trillions of other stars. Our sun would be just one faint star among billions in the local neighborhood. Our Earth would be undetectable without specifically looking for it. This perspective, this realization of how small and isolated we are, is not depressing, it's clarifying. It removes us from the center of the universe and places us in our actual position. One intelligent species on one planet orbiting one star in a galaxy of hundreds of billions of stars, in a universe of hundreds of billions of galaxies. From this perspective, the problems that occupy human attention are both gigantic and microscopic. They're gigantic because they affect billions of humans and millions of other species. They're microscopic because they occur on a tiny world in an indifferent universe. Yet from this same perspective flows empathy and unity. All humans share this one small world. All humans look up at the same stars. All humans are made of the same stellar material. All humans are participants in one grand cosmic story. Alpha Centauri represents the next chapter in that story. It's a destination calling to us, not with any urgency. The universe is patient, measured in billions of years, but with the persistent call of the frontier, of the unknown, of possibility. Whether or not we answer that call is up to us. Whether or not humanity reaches Alpha Centauri matters to humans, but it doesn't matter to the universe. The universe will continue its grand dance of stars and planets, whether or not any conscious beings ever traverse the gulf between worlds. But consciousness matters to consciousness. The fact that we exist, that we can think and question and wonder, means something to us. The fact that we might reach other worlds and meet other minds, or discover the absence of other minds, is profound to us because we are the ones doing the discovering. Alpha Centauri is waiting across the cosmic gulf. It doesn't know we're here. It doesn't care whether we reach it, but we know it's there. We care that it exists and that we might reach it. And that caring, that wonder, that drive to explore, that's what makes us human. Let me also discuss specific space missions and observatories that will contribute to Alpha Centauri observations in the coming decades, because these represent humanity's concrete plans for studying the system. The James Webb Space Telescope, currently in operation, is already providing valuable data on Alpha Centauri. JWST's infrared sensitivity reveals details invisible to visible light telescopes. Over the coming years, JWST will accumulate observations that will measure proper motion with unprecedented precision, improve measurements of stellar parameters, and potentially reveal atmospheric details of exoplanets through transit spectroscopy. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, will have capabilities for direct imaging of faint objects near bright stars. Roman's coronagraph instrument can suppress the overwhelming light of bright stars to reveal faint companions. If Alpha Centauri planets are bright enough, or if the orbital geometry favors observation, Roman might directly image exoplanets in the system for the first time. Such images would show the planet's colors, brightness, and potentially infrared signatures revealing atmospheric properties. Ground-based telescopes under construction will transform Alpha Centauri studies. The extremely large telescope in Chile, with a 39-meter primary mirror, will provide unprecedented resolution and light-gathering power. The giant Magellan telescope will offer similar capabilities. These facilities will conduct spectroscopic observations with sensitivity unmatched by current instruments, potentially detecting atmospheric compounds and biosignatures. The combination of space-based telescopes like JWST and Roman with ground-based facilities like ELT and GMT will create a comprehensive observational program. Each facility contributes unique capabilities. JWST excels at infrared spectroscopy. Roman provides direct imaging capability. Ground-based telescopes provide extreme resolution in visible wavelengths and detailed spectroscopy. Over coming decades, this combined observational effort will progressively expand knowledge of the Alpha Centauri system. Each new observation constrains models. Each detected planet refines our understanding of planetary formation. Each spectroscopic detection of an atmospheric component brings closer the possibility of detecting biosignatures. The technological advances enabling these observations represent centuries of cumulative human effort. Thousands of scientists and engineers have contributed to developing methods for detecting and characterizing exoplanets. The construction of massive telescopes required innovations in materials science, optics, control systems, and data processing. The satellite technology enabling space-based observation required advances in rocketry, orbital mechanics, and engineering. All of this effort converges on a few primary questions. What is in the Alpha Centauri system? Are planets common there? Is life present? Could we reach there? The answers to these questions, revealed through patient observation over decades, will shape humanity's understanding of our place in the cosmos and our future among the stars. Finally, let me address one last question. Why should we care about Alpha Centaurus if it's so far away and we might never reach it? The answer is that Alpha Centauri matters for reasons beyond whether we ever physically visit it. Alpha Centauri represents humanity's horizon, the frontier of our knowledge and ambition. It's the star that calls to us when we look at the night sky and wonder what lies beyond. Studying Alpha Centauri teaches us about other stars and planetary systems throughout the galaxy. Methods developed to detect and characterize Alpha Centauri planets can be applied to study systems farther away. Alpha Centauri serves as a testing ground for the science and technology that will eventually reveal whether life is common in the universe. Moreover, the pursuit of knowledge about Alpha Centauri unites humanity. Astronomers from dozens of countries contribute to Alpha Centauri observations. The data is shared freely among scientists worldwide. The questions driving Alpha Centauri research are universal questions about life, habitability, and our place in the cosmos. Even if humans never visit Alpha Centauri, the pursuit of understanding it changes us. It expands our perspective. It inspires technological development. It connects us to billions of years of cosmic history and connects us to each other. Alpha Centauri also represents possibility. It shows us that the stars, while distant, are not entirely beyond reach. With sufficient technology and determination, what now seems impossible might become possible. This possibility, more than any certainty, drives human exploration and discovery. In the end, Alpha Centauri matters because we exist, and we look up at the stars and wonder. The universe doesn't need us to explore it, but we need the exploration. We need the frontier. We need the goal that stretches our capabilities and inspires us to reach beyond what we currently are. Alpha Centauri will remain there long after we're gone, unchanged, indifferent to human ambition. But for now, in this moment, at this point in human history, Alpha Centauri represents our reach beyond Earth. It's a destination for humanity's long-term future, a challenge worthy of our best efforts, a star that calls to us across the cosmic gulf. Let me also take a moment to reflect on what makes Alpha Centauri different from Mars, another frontier that humanity pursues, because understanding these differences illuminates what Alpha Centauri represents. Mars is about 225 million kilometers from Earth on average, close enough that robotic rovers can be operated with only 3 to 22 minutes of communication delay depending on orbital positions. Human missions to Mars might take 6 to 9 months of travel time. Mars is rough, barren, and requires life support, but it's achievable with technology being developed today. Alpha Centauri is fundamentally different. It's not in our solar system. It's 40 trillion kilometers away. No amount of propulsion technology using conventional rockets will reach it in less than a million years. Future advanced technology, light sails, antimatter rockets, fusion drives might reduce travel time to decades or centuries, but this remains far beyond current capabilities. Yet, paradoxically, Alpha Centauri is more scientifically important than Mars. Mars is likely lifeless now, a frozen desert where life never emerged or long ago died. Alpha Centauri offers the possibility of finding life-bearing worlds. The stars at Alpha Centauri are brighter, more visible, and more accessible to study than Mars ever will be. The study of Alpha Centauri represents a different kind of frontier than Mars. Mars is a frontier we might traverse in our lifetimes with current technology. Alpha Centauri is a frontier we might traverse in centuries with advanced technology, or might study extensively through observation even if we never travel there. Both represent important directions for humanity. Mars offers a near-term goal for establishing human presence beyond Earth. Alpha Centauri offers a long-term goal for expanding human civilization beyond our solar system. Together, they represent humanity's dual impulses: to reach for the nearby frontier and to dream of the distant one. Understanding why we should care about Alpha Centauri, despite its distance, helps us understand ourselves. We are a species that looks beyond the horizon. We are driven by curiosity. We want to understand our place in the cosmos. These drives have taken us from caves to space stations, from the savannas of Africa to the moon. Alpha Centauri represents the next chapter in this journey. It's not a destination we'll reach tomorrow or perhaps even in our lifetimes, but it's a destination we can reach given enough time and technological progress. It's a direction we can point toward. It's a challenge we can work on. And in working toward Alpha Centauri, in studying it, building technology to reach it, training scientists and engineers, dreaming of the worlds there, we transform ourselves. We become more capable, more knowledgeable, more connected to each other and to the cosmos. In the final analysis, Alpha Centauri represents more than just a star system 4.37 light years away. It represents humanity's greatest ambitions and our deepest questions. It stands at the intersection of science and philosophy, technology and wonder, the present and potential future. When you look at Alpha Centauri through a telescope, when you read about discoveries there, when you contemplate the possibility of humans eventually reaching that distant system, you're engaging with something profound. You're asserting that humanity has the capacity to reach beyond Earth, to touch other worlds, to expand our civilization across the cosmos. Alpha Centauri is waiting. Billions of light years from the edge of the observable universe, billions of years old, and billions of years into the future, this star system will continue its slow orbit around the galactic center. Whether humans reach it or not, Alpha Centauri will be there, shining, potentially harboring worlds and life. But we get to decide whether to reach for it. We get to decide whether to pursue the knowledge, build the technology, maintain the vision across centuries. That choice belongs to us, to our civilization, to our descendants. Some might say the distance makes it futile to try, that humans should focus on problems closer to home. And there's validity to that view. The problems on Earth are real and pressing. Climate change, poverty, disease, conflict, these demand our attention and resources. Yet the pursuit of Alpha Centauri need not prevent addressing Earth's problems. Indeed, the technologies developed to reach the stars often find applications on Earth. The materials science, the power systems, the medical technology, the computer systems, these flow backward from space to improve life on Earth. Moreover, pursuing Alpha Centauri connects us to something larger than ourselves. It gives human civilization a long-term purpose beyond immediate survival and comfort. It inspires young people to pursue careers in science and engineering. It unites us around common goals. This is what Alpha Centauri truly represents, not just a distant star system, but a symbol of human potential, a reminder of what we might achieve if we maintain vision and ambition, a destination written in the stars that we might reach if we choose to pursue it. As we conclude this exploration of Alpha Centauri, we're left with wonder. Wonder about the stars themselves, about the planets orbiting them, about whether life exists in that system, about whether humanity will one day reach those distant worlds. Alpha Centauri has captured human imagination for centuries, not just since telescopes could resolve it into two separate stars, but since ancient times when humans gazed at the night sky and wondered what the stars were. In our own era, with our own technology, we can peer deeper into the Alpha Centauri system than anyone in history. Yet mysteries remain. The mystery is part of what makes Alpha Centauri precious. If we knew everything about the system, if we had observed every planet, detected every biosignature, understood every process, there would be nothing left to discover. The unknown calls to us. It drives our science. It inspires our technology. It connects us to an ancient human impulse to explore, to seek, to understand. The science of Alpha Centauri continues to evolve. New observations arrive. New planets are detected. New technologies enable deeper study. The story of Alpha Centauri is not finished. It's just beginning. The chapters yet to be written will shape humanity's understanding of life, habitability, and our place in the cosmos. You, reading these words, watching this video, you are part of that story. Your curiosity, your wonder, your desire to understand Alpha Centauri contributes to a global effort to study the star system. By paying attention to science, by maintaining an interest in space exploration, by supporting efforts to understand the cosmos, you participate in humanity's great project of cosmic discovery. Alpha Centauri is our next destination, not our next tomorrow, but our next century or millennium. It's the frontier that lies before us, the challenge that calls to us from across the cosmic gulf, the star that reminds us that humanity has a future extending far beyond Earth. The journey to Alpha Centauri may take centuries or millennia, or may never happen, but the journey of understanding Alpha Centauri happens now. Each observation, each discovery, each insight brings us closer to comprehending that distant star system and our relationship to it. And perhaps that is enough. Perhaps understanding can be as profound as exploration. Perhaps the discovery of knowledge is as significant as the discovery of worlds. Alpha Centauri awaits us. This closest star system to Earth, visible from the southern skies, home to worlds we can barely imagine, representing humanity's greatest ambitions and deepest questions about our place in the cosmos. It has been there for billions of years, shining steadily. It will remain there for billions more, waiting patiently. The question now is whether humanity will find the vision, the technology, and the determination to reach for it. Whether we accept this cosmic invitation and pursue the stars themselves as our future destination and home. The choice is ours to make, and the universe will wait patiently for our answer. Alpha Centauri is calling us across the cosmic distance. Will we answer that call? Thanks for watching.